So if you use Netflix or Amazon Instant Video, you know why streaming is really, really good, and you have every right to make fun of me and my substantial Blu-ray collection. I like living in the past because things are more predictable. But all of the conveniences of streaming are instantly passed on to the gaming side. For example, we have a thin client that basically runs on any streaming device. It doesn't matter. It's very nice because as a technology company, we don't need to sell hardware ourselves. So we are more than happy to take our client and put it onto anything that can take a video stream and connect a controller to it. We're not thinking about doing games on phones at this point because I don't necessarily want to play a game like Shadow of Mordor, which uses every single button on the PlayStation 4 controller and mapping that all onto like one iPhone or iPad touchscreen, because that's just, it doesn't feel good, believe me, I've tried. So the other nice thing is that we don't really have any dependencies on the CPU, GPU, or operating system. When I'm making a game, I have a very strict, I have very strict requirements on what I can use in terms of CPU, in terms of rendering. And that's kind of thrown out the window because we need to worry about that on our side as the cloud gaming provider. But on your side, you can have like the cheapest possible piece of hardware and it's going to run a game that looks like something that's running on a supercomputer PC. Also, if you set up your cloud game correctly, there are no load times. The session is up, the session is spinning, you basically click the button and it instantly starts. It's kind of like the old days when you would just plug a cartridge into your Nintendo 64. Also, you don't need to download and patch games anymore because we do that on the cloud side, it's all automated. Also, it's very hard to cheat or hack in a cloud game. This makes things very interesting for esports because no longer do we have to worry about people who are using game bots and other types of really sneaky low-level hacks that let you like see through walls or move faster or mess with the network systems. Also, streaming games makes piracy very hard. I'm not going to say it's impossible. I'm sure there's some weirdo future piracy that's going to affect cloud gaming. But for now, it's an open challenge, I guess. So let's talk a little bit about how the public loves streaming now and how the public is like just really into the cloud. The public is accepting of this. We all turn to the cloud for our movies, our books, our TV, but games are not quite there. They're only halfway. For right now, the games cloud world is essentially is basically a repository. We're able to throw large amounts of data to every client box, and then we can hold your save data for you up in the cloud in case like you spill Kool-Aid on your PlayStation or something. But we're seeing a lot more and more calculations being offloaded to the server, and a lot of mobile and free-to-play games are starting to do things on cloud side. So that's why we think that the move of all calculations to the cloud is pretty much inevitable at this point. The good news about it is we feel that we're at a point where the infrastructure has finally caught up to let us start exploring it. Before I go further, it is very critical that we have the talk. And the talk is about latency, because this is what everybody wants to know. So we feel that streaming has kind of gotten a bum rap since its inception. And like no matter how fast the frame time is on the server side, streaming games are always very much slave to the user's ISP. My boss Jacob, he lives in Manhattan. He has Fios right now. It's just screamingly fast. Now my dad, he lives in Amish country in Pennsylvania, and he's lucky to get like 3 megabit downstream. Like my LTE phone is faster than what he pays $60 a month for. So basically, if you give both guys a streaming platform, Jacob is going to think that streaming is awesome. My boss in New York will think streaming is awesome. My dad is going to be like, streaming games are garbage. I never want to deal with this again. But he doesn't know where the problem is coming from. Is it us as the streaming provider? Is it his ISP that's the bottleneck? So what we need to do is we need to enforce a quality bar with our platform. And what I mean by that is we are only going to be available on fiber services at the beginning because it guarantees the kind of latency that we need for high-speed video game throughput and action. We're working with infrastructure partners. We're figuring out the best places to put our server boxes. And we just want to ensure that we have just an amazing, like super low latency experience from beginning to end. We're going to be in Japan at first because it's very easy to cover all of Japan. In Japan, we essentially had to make 2 phone calls, and we covered the entire country in fiber for our service. So it was like easy. In America, it's a little bit trickier because America is a little bit bigger than Japan. We have done we've done a technical beta test in Japan. We partnered up with the NTT East, and we were able to do a beta starting in, I believe, in February, and I think it's still running now. We will be repeating that beta with some new special content for the Americas in Kansas City right here. It will be available for Google Fiber subscribers, and you'll be able to play it, you'll be able to get into beta this summer for free, and I will put up an email link for you guys to go to if you're interested in getting on board. Now, our strategy is kind of Tesla-esque in that we are not trying to hit all of America at the same time. We are going to start in kind of the high-spend metropolitan areas that have fiber available, and then we're going to start moving inward. This is a long game. We are not going to be able to cover the United States in a year, but we feel that we have to be the first to move. And it's going to be a very interesting journey for us. So we have two major goals in making a cloud gaming streaming platform. We need to make original content that takes advantage of the cloud because of that we're going to need like really, really great games. And to do that, we need to show what's possible. We need to get the tools ready to go. And we need to own that space by getting developers to make amazing content for us. Now, the second thing, and this is what my boss worries about, is the business side. How do we make it economical? So I need to go back in time a little bit, and I can talk about the guy who was actually making that happen at Shinra. Okay, so the guy in charge of this, his name is Tetsuchi Iwasaki. Iwasaki-san is here to build a future. He is not here to wear a suit. So the thing about Iwasaki-san is he is incapable of saying no. Back in like 1998, they went to him at Square Japan. They said, "Can you make an MMORPG using the PlayStation 2 as the basis and a modem that has a guaranteed throughput of 2.3 kilobytes per second and have thousands of players playing at the same time?" And he was like, "Okay." A couple of years later, many years later, the company Crytek that makes the game Crysis, just one of the most demanding games for PCs out there. They asked him if he could port the Crysis 3 engine to the PlayStation 3, a system that is considerably less powerful, and it kind of sounded impossible. It was just like, okay. And he did that. So 5 years ago, our CEO, Wada-san, he asked if he would figure out a way to make cloud gaming work by using supercomputers in the data center, and he very quickly said yes. So this brings us to the fun part, and we have to start asking ourselves, like, what actually is a supercomputer these days? This thing right here is called the K computer, and it's as good an example of any. It's a collection of, let me see, 80,000 SPARC 64 processors linked together with a 6-dimensional torus interconnect that is codenamed Tofu. And in actuality, there's really no good definition of what makes a supercomputer aside from a massive number of processors working together nicely. The question that we had to ask is, how do you get this thing to play a game? And can you in the first place? This one only plays tic-tac-toe, so it's kind of worthless. So what we're looking at here, there's a neat site called Top 500. And what Top 500 does is it provides a list of the highest powered supercomputers in the world. So we figured that this is a good place to start looking. Here are the top 10. You'll notice that we are seeing a lot of specialized CPUs like SPARC 64 and Power, but kind of within those, you're going to see the Intel Xeon technology, which is the traditional x86-based architecture that we all know and love. You can also see that the number one, the Tianhong, which is in China, is running off Xeon and both Xeon CPU and the Xeon FICO processors. This means that the Chinese government has something that can play Crysis right out of the box, which is a really good thing for them. So let's take a look at the co-processors. In addition, we're seeing co-processors like Xeon Phi. It's pronounced Phi if you're in a sorority and Phi if you're a mathematician. It's an evolution of the Larrabee architecture. And there are GPU-based accelerators in here as well, like the NVIDIA and Tesla boards with Kepler technology, and they're also creeping up into the top 10 as well. So what we're seeing here is it's a trend of general purpose processors being put to use in supercomputers, and about 85.4% of the top computers are Intel-based. Additionally, Amazon's EC2 is considered a supercomputer as well. But the biggest inspiration to our team was when we learned about this thing called the Dejima system. It's kind of like your double GPU SLI video game system at home, but kind of pushed to hilarious extremes. For starters, I want to point out that the Dejima system has the most sophisticated cooling system ever designed. And it was built by a guy named Tsuyoshi Hamada at the Nagasaki Advanced Computing Center. Now, the Dejima, it has a bunch of off-the-shelf NVIDIA GPUs that are kind of combined into this research supercomputer cluster. Now, they started really small with 32 GPUs, but then month by month, they started just buying more and going to the computer store and seeing what was cheap. And they wound up with a supercomputer that was 158 teraflops. And the shocker that came out of this was how incredibly cost efficient it was. And they wound up winning a Gordon Bell Award for cost performance. So the Dejima was like amazingly cheap. It was like $400,000. And for a while, it was like the greenest supercomputer in the world. Now, Hamada-san decided to swap out the interconnects to InfiniBand just for fun because he was bored, and then it kind of went up to 190 teraflops. So we believe that if the cost of supercomputing can be driven this low with kind of off-the-shelf stuff and architectures that we're already familiar with, why can't we use this for games? And this is how we wound up with our cloud gaming architecture. So this is great. I mean, we've determined that we can do render and compute in the cloud, and we can do it on architectures like x86 that we know how that works. Now the question is, can I afford, as a guy with business, to give one user a $400,000 supercomputer? And the answer to that is probably no. But the next question is, how do I actually make that cost effective? So server hardware is not cheap. As much as I'd like to grab a bunch of used like NVIDIA GTXs and just stuff them in a closet somewhere, we need to be using like enterprise hardware to actually get this stuff running. So we need to have very reliable stuff in a data center, and that tends to cost a lot of bank. So the deal here is that when we use PCs and consoles at home, we're not necessarily using them 24/7. There's a ton of downtime. We need to use that downtime, and it's not that we don't want to have a bunch of processors idling, but it's more along the lines that we want to have our processors running at 100% all of the time in order to be cost efficient and getting our money's worth from the server hardware that we're renting in the data center. So that means if we have 5 glasses that are 80% full, that means that we have one completely empty glass. And that's bad for business. So if you look at how the traditional streaming architecture works, we basically have virtual machines. So what we do is we traditionally kind of have one user assigned to a number of CPUs and GPUs. For that reason, we have all of the inefficiencies of running the game locally, which isn't a problem locally, but again, it's a problem in the cloud. Now, because of those inefficiencies, it turns into a very, very high cost per user. And that turns into angry posts on the internet when they reveal their pricing model. And so what we have to do for let's look at a traditional DirectX game. The CPU and the GPU here are not being maxed out all the time. Now for a box that's underneath your TV, that's fine. But for a cloud game-based virtual machine, that's a problem. So what we need to do is maximize the CPU and the GPU at all times so it looks more like this. So how do we do that? Our solution was to actually physically chop the CPU away from the GPU. And we essentially create a sharing economy for video games. So once our technology splits the CPU from the GPU, it balances the game process and render processes against what's potentially dozens or hundreds of users on a single CPU server, and even more users on a single GPU server. So the more players that we can add, the more we scale, and the better the games. The end result is we're able to share a supercomputer among players in a way that it actually works out. So we also want to make sure that you can run pretty much any Windows, DirectX 9, DirectX 11, and in the future, DirectX 12 game in the cloud natively. We don't want you to have to go out and start doing weird stuff in OpenGL and Linux. I mean, I like Linux, but game developers like what they're familiar with. And for most game developers, it's Windows and Gighacks. So we want to have the ability to run this stuff without you needing to rebuild the game or do anything particularly tricky. So you know how it works with a local console. And you know how it works with a console in the cloud. What we do in a traditional game is we receive player input, we send it to the game exe, video card does the rendering, it spits it back to your monitor. When we traditionally run a game in the cloud, it's essentially the same thing, except when the video card makes the final image, it compresses it and sends it back over the internet. What we do, and where we start getting tricky, is the game will pull all of the draw commands out of the game, and it ships it over a high-speed interconnect to a separate rendering server that makes the final frame, and then it spits it back to you as a video stream. So let me kind of explain a little bit. Let me get into the guts of this a little bit. The way we do this is we use a fake DLL. We replace a single file, and we make it think that it's talking to a video card when in fact it's talking to a separate render server. So let's look at the benefit here and the kind of sharing costs that we're able to save. If we run the game standalone on a supercomputer rack, we're averaging about 9 milliseconds per frame. But if we run the game under the Shinra architecture and we start sharing things like textures, like commands, we managed to cut that down to 4.4 milliseconds. Now, how is that even possible? The trick is that our protocol lets us do more things like synchronous calls. It lets us put data in memory where DirectX doesn't usually let you. We also cache the results of operations between multiple users. So when we run this at scale, this means we can kind of get double the players into a single configuration as if we were just running it traditionally. I'll just kind of skip over this, but GPU RAM is very expensive. So we found a lot of cost benefits from sharing texture caches. So for example, if a lot of people are playing Deus Ex, we're going to make sure that they're running on the same servers so we can maximize that resource sharing, and they can pull things out of a common texture pool. So I can show you right now one of the earlier demos that we have. Let's see here. Okay, so this is all running on a single server PC. At the upper left, we have 16 instances of Mini Ninjas. We have 9 instances of Deus Ex because it's a little bit more graphically demanding title. Bottom left, we're seeing Dragon Quest, 16 instances, and then we have Mini Ninjas down here, also 16. So we've got a ton of games running on a single server box, and it's streaming all of this out at once. So this was like a good starting point because we were able to get existing titles and just kind of port them, one-to-one over to our architecture without really having to do too much heavy lifting.
Can you run that again?
Huh?
Can you run that again?
Yeah, sure. So in this example, one screen is equal to one GPU, and this is pretty old. This is from 2013, and it was running on inside this box there were 4 Quadro K5000s, which are by now they're old and busted and yesterday's news. So our numbers have increased once we start putting things like Titan Blacks and the new GTXs in there. The numbers just increase. So yeah, just one PC, one server PC, making lots of people happy. Making Okay, so because the system works so well with older content, and it's easy to get older stuff up and running, we're currently looking for back catalog content to launch on the system. Porting stuff over, it takes just a couple days, or maybe it might take a little bit longer if it's a new engine or some technology that we haven't seen before, but we handle all of that on our side. We may have some questions about the code. It makes things easier. We have ported games that are incredibly demanding and terrifying from a technical standpoint without any reference to the source code where the original programmers had left. So we won't have a problem with it. It's just how crazy do you want to drive our programmers is the question. So the result is current Windows games, they run fine on Shinra technology. But that's not the cool part of what we're doing, and we can make things a lot more interesting now that we've got all those supercomputer guts in one room. So we've kind of we found a break-in design here, and what we're calling it is supercomputer multiplayer. So when you make a video game that's played online, you have to make you kind of have to make a lot of you have to make a lot of serious changes to the game to get it running with multiple players. We have to make sure that things remain static. It's really hard to change large chunks of the game world and kind of synchronize all that data across a bunch of players. So something that our R&D department has been looking into is creating game worlds that are really dynamic on a massive scale. And this is the architecture that we are most excited about. And we're calling it a 1 to n architecture. And what this means is we have one supercomputer over on the left that's handling all of the calculations for a single game's multiplayer instance. So we have a game world of really amazing fidelity that is extremely dynamic, and each player is not running that on a local machine. It's all happening on one it's all happening on one supercomputer. And my kind of ghetto illustration here is showing how you have your game world, and each player is essentially just opening a FaceTime window into the world. So this world is being calculated in one place. There's only one process, and all the calculations are being shared. So the way that this works is we have a single instance of the game engine running, and all players, all interactions, all calculations, they all happen within the same world, and they only happen once. That means that your physics are shared, your AI is shared. And it's kind of like you're doing a local split-screen game in terms of the way that you would write your game. It's just on a much larger scale. Again, calculations are done once. And this means that the need to write really intense synchronized network code, it's gone. It's out the window. It doesn't exist anymore. So that is pretty major for a lot of reasons. We can break a building into a couple thousand pieces, and those pieces aren't just going to disappear after 30 seconds. Like everything can have physics on it. It sticks around. It's persistent. It's not just aesthetic, and it's very easy to change the world and not have it reset later. So here's the game developer's dilemma. This is the problem that we always have. We have one CPU, we have one GPU, and you've got to divide that so it's presumably going to work on the cheapest netbook with terrible Intel integrated graphics from 1999 with Windows XP with no service packs installed. That's your basic pot, and it's got to run on that. So what Shinra development does is we open up the abilities to basically order more pods. We can start doing things like offloading, rendering, AI, physics. All of that stuff can be done on different boxes, and then we can have this dedicated hardware that's going to pump back into the main game process. And then again, all those calculations are shared, they're done once. So also, if you are really good at multi-threaded code, this will work very well for you. So let's talk about what a big game would look like on here. So what I'm going to show you next is our demo from this year's GDC. And let me put this here. I am not Alex Tate, the project manager. I wish I was. Wears very nice clothes. So what we're looking at here is this is one game world. What you're seeing right now is a total of 64 windows that are being rendered on one supercomputer PC into a single game world that has been created by us. Now the scale of this is very large. What you're looking at is a 20-mile by 20-mile landmass. All of this is in memory at once. So it's not the case where you are, this is not the case of a game where you're constantly streaming in chunks and chunks of the world because your console only has so much memory. In this, we're running it on a supercomputer that just has boatloads of memory. So all of this is in memory at once. You can fly across the map like as fast as you would ever want without the game needing to catch up. It's also really nice for users because there's no loading to get into a game like this. And also, like in a lot of games, like you'll go to a building and maybe there's going to be a very complicated interior scene. So as soon as you open the door, there's a load screen. This is the kind of technology where we want to make that no longer exist. Also, the world is being rendered out with about a total of 1 million trees. So we're able to basically just push the entity count and just put lots and lots of stuff into this world. So in addition to being able to draw a ton of trees, we can also kind of push that type of scale over to things like player characters and AI. So I'm just going to zoom it here. Oh, actually, turn it down. Yeah, there we go. Okay, so if you look at the upper right here. Oh, by the way, each screen we're just rendering this way just so you can get a scope of how the game is multiplayer. But each screen is running on a separate monitor. in our normal demo for this.
Are these all 4 players in the same world?
Yeah, everybody here is sharing the same world space, and we're looking to right now it's at 4 just for demo purposes, but we can increase that number very easily. So these guys here, all of the dragons, these are not particles. None of this is pre-calculated. All of the dragons are running their own individual AI. So they have flight paths, they know how to flock, and one of the features we added is the ability to call a bunch of dragon buddies and have them fly around with you. So I think one of the 4 clients is going to have the other. So this guy is going to have some friends to tag along with him. Okay, so let's see. One of the other key features of our system is terrain deformation. If you look at the upper left. So we have the ability to kind of take the game world and start, extracting it, modifying it, and then having this is actually very difficult to do in a traditional network model, just because the actual data set of the world space, the height map, takes up a huge amount of memory. And it's really, really hard to do these calculations and pass those across all the clients who are playing at once. The other cool thing is this is visible. This is all visible from wherever you are. Because there's one height map, this is all in memory, no matter where you are inside the world. So this guy, can see this kind of stuff happening, even if he's like, a mile away. We also have some very simple physics running on top of things. When the mountains come up, we have rocks that are just kind of rendering. We didn't really go crazy on the physics for this, but we ported the bullet. Bullets, I think it's a CPU-based physics system, and now it's running multi-threaded in this existence. So that's kind of cool. And we were like, okay, so we've proven out the ability to do lots and lots of AI entities flying around. We can do a gigantic environment with no load times. Okay, this is all neat. What else can we do? So we have a guy on staff who is known for his complex fluid simulation software. So what we can do is he created a fluid simulation where we are offloading the calculations to a single NVIDIA Titan block. So if you look here, all of these dragons have the ability to lift their legs into the air and produce water, or produce fluid. And we'll start to see, there we go. So as we can see, this is an instance where we are offloading fluid simulation to a GPU. And yeah, now we have a live fluid sim that is running on top of a 20 by 20 map. And obviously it's taking the height map into account, so it'll flow down realistically. This is not pre-calculated. We're able to do this kind of thing anywhere in the map, under any situation. So in other games you would have to do the heavy lifting. You would have to do the math by pre-calculating it, and it would always happen the same way. In this, because we've got the ability to simulate so much mathematically complex stuff on extra boxes, we can create unique situations and start running simulation-based gameplay that is going to have really different results every time you play. So let me just jump ahead a little bit here. One of the unique features of the water is that it is interactive. So the actual entities are able to feed back into the simulation, so it's not just a static one-way simulation. So these guys, the guys that you can kind of like bounce down the water and watch the splashes as you hit it. So in a lot of come back, Shane. There we go. So yeah, so because this is all running live. It's not just like a flat plane of water where you can't really interact with it. We actually have wind that's blowing on the water and making ripples. And when these guys are kind of like doing the motorboat thing and zipping around, they're leaving wakes and affecting the whole simulation across the entire sample space. So what happens when you take our ability to raise mountains and then you combine it with fluid simulation? You get tidal waves. So this is kind of one of the interesting results we had when we started layering our different simulation layers on top of each other. So as you can see, we've got guys pulling multiple mountains out of the ground, and then the resulting tidal waves are actually hitting each other and interacting with each other in ways that we just are not used to seeing in games. So yeah, this has been like a really big hit when we actually have the live demo. It's just super awesome to make these gigantic title things. And we're working on an upcoming game that is kind of putting a really big emphasis.
Is it How to Train Your Dragon?
We should talk to those guys.
Yeah, I've seen this, yeah.
But yeah, this is the kind of like cool stuff that we're interested in.
What engine is this?
Okay, so the team that made this is a very small team. We started out originally with 2 guys working for about 6 months. Then we kind of upped it to they got the basic world space up and running. And then we had a total of 5 programmers working for 6 more months, and they brought on the terrain deformation system, and they implemented the fluid sim. So it's not like gigantic team of like 100 people working on this. It's nice because there's really not a lot of if any network code in here. So yeah, it's doing things that is completely impossible.
And if we're on IGN, how do we search for this video? When do we search for?
Just search IGN Shinra GDC, and we probably have a link up to it. Right? Thanks, IGN. Thank you, IGN. So that's kind of the that's kind of what you would look for. We're looking for in terms of creating like big games, like kind of that AAA experience. But again, we're just technology guys, and what we need is awesome developers to jump on and get inspired by this kind of stuff and say, hey, we can do better than that. We're like, really? Okay, please. But there's also indies. Like, are there any indie programmers in the house today? Any game? What can a person do if they're just like a single indie game programmer? What if you don't live in Kansas City? What if you don't have a supercomputer that you can make stuff on? Like, what if you live here? Like, this sucks for you because you can't, can you not take advantage of what we're doing? So we kind of planned out a thing called the Shinra Community CDK, or Cloud Development Kit. And it's a simple toolkit for making things like 2D and possibly 3D cloud games as well. It works with any repository. We are distributing it via GitHub. And with this system, you're able to create and test your content locally. And then eventually you're going to be able to just do an automated push up to our servers to test inside a multiplayer environment. We're going to be supporting it via GitHub and via Facebook pages. This is coming out in 2 weeks. In Japan, we're going to be kind of running the beta of the SDK, and the English version is going to come a little bit afterwards. It's going to be shipping it's going to be shipping as a bilingual Japanese and English SDK. I worked in video game localization for 10 years, so it's going to be very, very clean and very, very nice to use. So here's an example of a game that you could make in this system. And this is a little game called Space Sweeper. And Space Sweeper is kind of rad. Okay, so Space Sweeper was made by one guy who lives kind of out in the boonies of Japan. And he has kind of crappy internet. So it's not like he can test this kind of thing very easily in a big, in a fiber-connected cloud environment. So here's what we're looking at. This is a massively multiplayer 2D shoot 'em up. Right now you see one player, but this is scalable up to hundreds of players. And what makes this kind of a really good example of what you can do in the cloud very easily is that there are tens of thousands of moving objects and hundreds of players at once. And typically, the requirements that you would have in order to move that much data around across all of those clients at once is something that is not really achievable for any one-man team. So the indie SDK that we're doing is kind of out there to let people start making really big, really interesting multiplayer games without necessarily needing to be, black belts in network programming, because those people are few and far between, especially one-man teams. So basically, in the end, we have 3 architectures. We have the ability just to take your existing cloud games and just put them in the cloud. We have the ability to make small indie games, like Space Sweeper. And then if you want to go big and go crazy, you can do things like our R&D demo with the tidal waves and the dragons. So when can you play this stuff? And the answer is soon. We're talking to developers right now. Our closed technical beta has been running in Japan. Our technical beta will start right here in Kansas City this summer. We will be on the PC at the beginning. We would like to expand that to set-top boxes. Anything that will play videos, anything that you can hook the controller up to is fair game for us. So yeah, we have a platform. It uses fiber. It runs Windows games for developer friendliness. And we want to explore what cloud supercomputer gaming is going to be able to create. And the question that I ask all developers is, what would you be able to make if we gave you unlimited CPU and GPU? I'd like to open it up. Thank you much for showing up. By the way, Simon Ferrari, fresh from the New York City Game Center, is here. He is our new Director of Indie Partnerships, and he will be handling all of our indie gaming communication for the company. So please feel free to check in and say hello. My email is up there, and so is Simon's. If you want to sign up for our for the technical beta here, it's going to be available to Google Fiber subscribers. Please send a mail, and that will send you an invite and a reminder as soon as it goes live later this summer. So if you have any questions, please, I'm